And as time goes on in the coming weeks, it's coming out away from the sun. When it was closest to the sun, we couldn't look at it because the Earth was on the opposite side. But in the coming weeks leading to December 19th, that's when it will be closest to Earth. We should learn much more about it. And it's exciting to look at the other side. My hope is that on December 19th, when it comes closest to Earth, it will not deliver any unwanted gifts for the holiday.
As 3I Atlas sweeps back through the inner solar system, the interstellar wanderer once again ignites a wave of anxiety and fascination. Dramatic new images show the comet flaring with unexpected jets, shifting in color, and forming an eerie sunward anti-tail unlike anything seen in most comets. With each update, the question grows louder. Is 3I Atlas posing a threat to humans? What's fueling this renewed concern are the unexpected changes detected around and after perihelion. Instead of fading or breaking apart, as many fragile comets do under intense solar heating, 3I Atlas has emerged even more active. High-resolution observations reveal multiple collimated jets, including a sunward jet nearly 1 million kilometers long and an anti-solar extension stretching 3 million kilometers outward. These are not the chaotic plumes typical of a dusty, crumbling nucleus. These jets appear organized, persistent, and far stronger than the norm. Even more unsettling is the object's lack of fragmentation. Despite predictions that 3I Atlas should shed mass or split after its close solar pass, the nucleus appears to remain a single intact body. No major debris field, no structural collapse. Instead, the object shows a surprising degree of cohesion and resilience, raising questions about its composition and internal strength. For an interstellar visitor subjected to extreme heating, this behavior is anything but ordinary. Then there's the sunward anti-tail, a rare and visually striking feature that has now become one of 3I Atlas's defining signatures. Unlike a typical comet tail blown away from the sun, this structure points directly toward it, suggesting unusual dust grain sizes or complex outgassing patterns that challenge standard models. Combined with the sudden brightening and the intense jet morphology, the object's appearance has shifted from merely intriguing to profoundly enigmatic. What these changes actually mean, and whether they hint at something benign, natural, or truly unprecedented, remains uncertain. The full answer lies deeper in the data, and the truth will unfold only as we examine the strange behavior of this interstellar visitor piece by piece. Loeb's latest analysis adds yet another layer to the mystery.
Some observers noticed that it has a set of jets around it, more than 7. Some headed towards the sun, some away from the sun. It's a spectacular view that we have right now after it passed closest to the sun on October 29th. It became bluer than the sun. It was 5 times brighter than it was before it came close to the sun.
Wow.
So the action is happening right now, and in the coming days and weeks, we should learn much more about it.
After examining the scale and structure of the jets erupting from 3I Atlas, he concluded that the object simply doesn't possess enough surface area to sustain the volume of material being blasted into space. A natural comet, even a large one, cannot physically support that level of mass flow without rapidly eroding or fracturing. Yet 3I Atlas remains intact and astonishingly active.
The sunward jet in particular defied simple explanation. For material to form a tail directed toward the sun, the dust grains involved must be relatively large, heavy enough that solar radiation pressure cannot push them outward. These grains would have to be ejected at exactly the right velocity and at exactly the right angle, creating a configuration so precise that it has only been documented a handful of times in the cometary record. But even those rare examples occurred in long-period comets from our own solar system, whose internal makeup, age, and evolutionary history are at least partially understood. With 3i Atlas, scientists are dealing with an object forged in a distant star system, its chemistry and physical structure potentially wildly different from anything we consider familiar. The lack of fragmentation only deepened the mystery. Most comets that dive toward the sun experience tremendous stresses as their surfaces heat unevenly. Internal pressures spike, cracks form, and in many cases, the nucleus splits into smaller pieces. For 3i Atlas to endure this phase without obvious structural failure demands a level of resilience that few comets possess. Some researchers have suggested that the object may contain a higher than normal proportion of metals or compacted rock. Others argue that its structure may have been hardened during the long interstellar journey as cosmic rays gradually altered its outer layers. But none of these hypotheses adequately explain why the comet not only survived, but intensified its activity, flaring with even greater power in the days after its closest approach to the sun. Complicating matters further is the growing debate surrounding the flow of observational data. As 3i Atlas made its passage through regions where several spacecraft and planetary probes had an unobstructed view, many scientists anticipated a flood of high-resolution images, particularly from instruments designed to capture fast-moving or distant targets with exceptional precision. Among these was the Mars Reconnaissance Orbiter's HiRISE camera, a device capable of photographing objects as small as a dining table from orbit around Mars. Because 3i Atlas passed within a range where such instruments could theoretically track it, researchers expected at least a handful of detailed frames, revealing the true structure of the comet's nucleus and its complex jets. But as days passed and lower-resolution ground-based images continued to circulate online, something conspicuous remained missing: the spaceborne imagery. No high-detail surface scans, no close-frame nucleus shots, no close-up of the sunward anti-tail, none of the material that could instantly confirm or refute theories about fragmentation, jet alignment, or structural integrity. The silence was noticeable, and for a public already primed by sensational headlines, it didn't take long for speculation to surge. Why were amateur telescopes producing nightly updates while instruments millions of miles closer had produced nothing for public release? Was the delay technical, logistical, or did the data show something researchers weren't ready to interpret openly? Official explanations pointed to bureaucratic slowdowns, backlogs created by government shutdowns, reduced staffing, procedural delays in image processing pipelines, and the careful vetting required before NASA releases any publicly archived imagery. These reasons are not unusual. Spaceborne datasets often take weeks or even months to move from collection to publication, especially when they compete with higher priority planetary science imaging. But the timing could not have been more problematic. The comet was changing rapidly. News outlets were covering every flare and twist in its behavior, and the public attention on 3i Atlas was magnified by its exotic interstellar origins. In that vacuum of information, theories bloomed. Some insisted the spacecraft simply missed the target. Others speculated that the images were being held back because they contained something anomalous. Researchers, too, grew impatient. Astronomer Avi Loeb, known for closely tracking interstellar objects, publicly voiced his frustration. For him and other scientists attempting to model 3i Atlas in real time, the absence of the most detailed imagery wasn't merely an inconvenience, it was a barrier to understanding. Loeb argued that timely access to these datasets is not optional when interpreting behavior as unusual as sharply collimated jets, antitails, and unexpected post-perihelion brightening. Without the highest quality data available, researchers are forced to rely on interpretations built from incomplete pictures and inconsistent resolution. The limited imagery also means that even subtle clues, microfractures, rotational cues, small-scale dust plumes, or jet source regions remain unresolved. These nuances matter. They can distinguish between natural outgassing and unusual processes, between a structurally stable nucleus and one on the verge of collapse. To scientists attempting to keep pace with a fast-evolving interstellar object, every withheld frame feels like a missed opportunity. And so, in the absence of clarity, a familiar tension emerges: the space between what is known, what is suspected, and what is imagined. The missing images don't prove anything extraordinary, but they don't rule out anything extraordinary either. As long as the highest resolution views of 3I Atlas remain inaccessible, the debate will continue to sharpen, fed by a mixture of scientific curiosity, public fascination, and the undeniable allure of a mystery unfolding millions of miles away. Meanwhile, the comet's brightness surge created a striking shift in its appearance. During the weeks surrounding perihelion, 3I Atlas brightened far more than initial models projected, taking on a bluish tone in some filters, likely the result of carbon monoxide ions fluorescing in the solar wind. The extended tail structures seemed to evolve almost nightly, bending and reshaping as the comet rotated and as the sun's radiation sculpted the stream of dust and gas trailing behind it. Observatories reported changing surface textures and brightness variations that hinted at active regions opening and closing on the nucleus. Each new dataset raised questions. Was the comet undergoing a controlled evolution? Was it venting from specific locations? Why did the behavior remain so consistent despite the expected chaos of perihelion dynamics? As curiosity spread, so did unease. Online communities latched on to the comet's unusual features, drawing comparisons to Oumuamua's non-gravitational acceleration and Borisov's anomalous dust behavior. Speculative videos and posts suggested that 3I Atlas might be maneuvering or displaying characteristics inconsistent with a purely natural object. Yet even within academic circles, there was acknowledgement that 3I Atlas was not behaving like a typical icy body, at least not one formed in our solar system.
Part of the fascination with interstellar objects lies in how little we know about them. Each visitor brings with it clues about how planets, stars, and disks of dust and gas behave outside the boundaries of our own cosmic neighborhood. But with 3I Atlas, the clues feel particularly cryptic. The stable structure, the persistent jet alignment, the sunward anti-tail, the delayed brightening, all of it forms a puzzle that doesn't quite snap neatly into the usual comet categories. It challenges assumptions about how interstellar material evolves and how these objects respond to the extreme forces at play when they plunge through a new star system for the first time. Spectroscopic measurements, which could help determine the speed of the jets, remain incomplete. If the jets mimic natural outgassing, their speeds would be on the order of a few hundred meters per second. But if they exceed that by a significant margin, creeping into the kilometers per second range, they would suggest physical processes not easily explained by standard cometary physics. Researchers around the world are racing to secure observation time on major telescopes for Doppler velocity measurements before 3I Atlas dims beyond reach. These readings will be crucial in determining whether the jets are simply powerful releases of volatile gases or something more unusual. Even without those measurements, the comet's behavior has forced scientists to reconsider what normal means when describing an interstellar object. The handful of such visitors we have observed, Oumuamua and Borisov being the most famous, already fall outside the typical boundaries of comet and asteroid categories. Oumuamua lacked a coma, yet accelerated without visible outgassing. Borisov behaved more like a typical comet, but displayed a dust grain distribution that proved hard to reconcile with models. 3I Atlas now joins this small but significant group, carrying its own set of mysteries and defying easy classification. As days turn into weeks and the comet slowly pulls away from the sun, the world continues watching, waiting for the next round of data to explain or deepen the enigma. The persistent jets are still visible, the nucleus remains intact, the anti-tail continues to stretch sunward. All the while, its trajectory carries it silently across the sky, an emissary from a distant star system whose secrets remain buried beneath layers of dust, ice, and speculation. Only in the final analysis of all these observations, its path, its behavior, its unexpected resilience, will the question first posed at the outset finally be answered. For now, 3I Atlas remains suspended between fear and wonder, between scientific curiosity and public anxiety, between what we understand and what we only think we understand.
And the truth about whether it poses any danger or whether its mysteries lie only in the physics it carries from another star will emerge only as researchers peel back the last remaining layers of this extraordinary visitor from the interstellar dark.